This lesson is on section 3.3, polygons and their angles. So first of all, the definition, what makes a polygon a polygon? It's a closed figure that's made up of 3 or more segments that connect only at their endpoints. Okay, so some examples of what a polygon is would be anything that doesn't have curves. So you could have a polygon that's funky shaped. That would be a polygon because all it's got is segments that connect. Well, they're supposed to connect at their endpoints, I guess. That didn't really work so well, did it? But that's what makes a polygon a polygon. Okay? No curves and no crossing. For example, you couldn't have this. This is not a polygon because they intersect at more, the segments intersect at more than just their endpoints. And you couldn't have anything that looks like this, okay? Because even though it does have some segments, it has curves. So those would be wrong. That one would be correct. Naming, as far as naming polygons go, you name them by their corners. You can either go clockwise or counterclockwise, but order does count. Okay, so you can pick any letter you want. Your book would name this polygon A, B, C, D, E, F. It likes to be alphabetical if possible. But you could just as easily name it C, B, A, F, E, D. You can start at any vertex, and you can either go clockwise or counterclockwise. It makes no difference. Some kinds of polygons that you can have, there are equilateral polygons. Equilateral meaning all the sides are congruent. Okay. In this case, this would be a rhombus. This would be an equilateral hexagon. Equiangular means the polygon simply has to have all angles congruent. So a rectangle would be a good example of equiangular. You can combine those two. If your polygon has equal sides and equal angles, then it is what we call a regular polygon. That would be your equilateral triangles, squares. Most of the shapes that you think of when you are drawing shapes. When you think of a hexagon, this is kind of the picture that you see, but you'll want it more equiangular than that. If you think of shape sorters, those toys you had when you were kids, and you had to put the shape inside the ball or the car or whatever that had the hole, so you had to find the right size hole. Those usually are regular polygons because they're easier for the small children to get right than they are if they're irregular. Polygons can be convex or concave. If they are convex, that means that all the vertices are on the exterior of the polygon. So, in other words, if you drew a circle or some kind of rounded figure around this, you would be able to hit all of the vertices. Okay, that's what makes it convex. Same thing here, I should be able to draw a circle and hit all of the vertices. If I could draw normal, that wouldn't be helpful. Concave means that at least one of the vertices is on the inside. For example, when I draw a circle around the star and try and hit all the corners, I miss 1, 2, 3, 4, 5. So this is concave. Same thing here. If I drew a circle around, I would miss this one and this one. One way to remember it is concave means that part of it is caved in. So when you draw it, the polygon, some part of it goes inside the rest of it. That's a good way to remember it. For the most part, we only talk about convex polygons. They're the ones that follow the rules of geometry. Concave ones do not usually follow the rules. So other than being able to name them and look at their symmetry, that's pretty much all we do in terms of concave polygons. Okay, now this is a big chart. It talks about the names for each of the polygons up through 12 sides. that have been created. It gives an example of what it might look like, and it gives the angle measures for the inside of the angle and the outsides of the angles. The outside angles. So for example, we already learned that the interior angles of a triangle added up to 180. What's interesting is that the exterior angles, these angles that are sitting on the outside here, those, if I look at 1, 2, 3 of those, the 3 exterior angles have to add up to 360. Notice that for each time you go up by 1 side length, it goes up by 180 degrees. And we'll get to that in a minute. But notice the exterior angles stay the same no matter how many sides your polygon has. So the total of the exterior angles is always 360 no matter how many sides it has, but the interior angles for 3, that's our smallest one, starts at 180 and it goes up by 180 each time. The reason it goes up by 180 each time is really based on the idea of triangles. Each triangle, we know, the interior angles have to add up to 180. Well, every time you add a side, you can still split it up into triangles. For example, if I drew a line from this vertex to this vertex, it splits it into 2 triangles. If I would have drawn that line correctly. It splits it into 2 triangles. Each one has to be 180. Therefore, together, all those angles on the inside would have to add up to 360. A pentagon can be split up into 3 triangles, so 3 times 180 would give you 540 total degrees. A hexagon splits up into 4 triangles, each one at 180. 4 times 180 is 720. Notice that for 6 sides, it makes 4 triangles. For 5 sides, it makes 3 triangles. For 4 sides, it makes 2, and for 3 sides, it makes 1 triangle. There's a pattern here. If you use your inductive reasoning skills, you can see that it makes 2 less triangles than it does sides. So for a 7-sided figure, it would break up into 5 triangles at 180. Octagon, 8 sides, would be 6 sides at 180, and so on. So there, you can always find the total number of sides, or total number of degrees inside a polygon by looking at the number of sides it has. All you do is take the number of sides and minus 2 from it. That's how many triangles it creates, and then take your number of triangles times 180, and that will give you your total for your interior angles. This is a formula that we will use often, so make sure that you write that down in your notes. Each one of these has its own name. You probably have heard, triangle, quadrilateral, pentagon, hexagon, heptagon, octagon. 9 sides is nonagon. 10 sides is decagon. 11 sides, they did not create a prefix for 11, so it's just 11gon, and then 12 is dodecagon. Anything above 12, we use the number of sides it has. So for example, for 13 sides, we would call it a 13gon, just like we do for 11. 14gon, 15gon, and so on. So let's look at a couple of examples using that chart that we just looked at. Okay, so if each exterior angle, let's say you had a polygon that had an unknown number of sides, so it's just some random polygon, blah, 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 blah. That's not really much of a polygon, but you know what I'm talking about. You don't know how many sides it has. And each exterior angle is 10 degrees. Can you figure out how many sides it has based on the fact that the exterior angle, now these are regular polygons, so all the angles are the same. I guess I didn't write that in, did I? Each exterior angle is 10 degrees. Okay, well think about that. What's the total of the exterior angles have to be in any regular polygon? 360. So if each one is 10 degrees, how many exterior angles are there? Well, you'd take 36 divided by 10 and it would be 360 divided by 10 and it would be 36. So that's how many exterior angles it would have to be, so that's how many sides it has to have. So we would call it a 36gon. And then to figure out your interior angle, you can do that a couple of ways. You can do it how we just did it, do the n-2. So since it's a 36gon, it makes 34 triangles, 34 times 180. and then you would divide that by 36 because there's actually 36 angles. An easier way to do that is look at the relationship between an interior and an exterior angle in any polygon. The relationship is they have to add up to 180. So if the exterior angle is 10 degrees, the interior angle would have to measure 170, so that together they make a straight line. Another example, what if I give you that the interior angles are 167 degrees? Well, going from the exterior angles to the interior angles, which one is easier to use? Well, exterior angles, especially if you don't know how many sides the polygon has, because you know the exterior angles still have to add up to 360 regardless of how many sides it has. So if the interior angles are 167, the very first thing I would do is flip that over and say, okay, then what do the exterior angles have to measure? The exterior angle measures would have to equal 13 because together they have to be supplementary. And now you can go back and do it exactly the same way you just did. If each exterior angle is 13, you'd take 360 divided by 13, and you get 27.7. So it would have 27.7 sides. A regular polygon would not have a 0.7 of a side because that wouldn't make it regular. It would be irregular. So to name this polygon, we would say DNE, which means it does not exist. There is not a regular polygon that has 27.7 sides. So you have to work with all whole numbers for the most part in terms of regular polygons and their angles. That's not necessarily true all the time, but for the most part, especially when it comes to the number of sides, you have to have a whole number in terms of the number of sides. You can't have point anything of sides. There are angle measures that are 0.5s and those kinds of things. Okay, so some more examples. They want you to name this polygon and classify it as convex or concave. Okay, so the first thing you have to do is number your sides. 1, 2, 3, 4, 5, 6, 7. It has 7 sides, so it is a heptagon. And as far as convex or concave, if I drew a circle around it, this vertex for sure would be on the inside of the polygon, which means it is concave. So we would call this a concave heptagon. Another kind of example that you're going to see in your homework is they're going to give you a polygon with some angle measures, and you're going to have to find the ones that are missing. In order to do that, you have to know what the total of the interior angles are. Okay? And in order to do that, you have to know how many sides it has. So we count sides, 1, 2, 3, 4, 5. It is a pentagon. Okay, so as far as interior angles of a pentagon, you can go back to your chart if you need to. So the total of the interior angles is 540. So you'd take 540 and you would add up those 4 angles, and to get your, you'd add up the 4 that they give you. So you'd add 99 to 106 to 81 to 151, and that would give you a total of 437, and then you would subtract that from 540, and you would get 103, which means that what's left for this angle is 103 degrees. Okay, those are some examples of the kind of homework you're going to see today, and your homework assignments are as follows.